Okay, using sum and difference formulas. So there are a bunch of sum and difference identities that we can use to find the exact measure of different angles. So I'm just going to skip forward in the notes a little bit. Let's say we had a problem like this, okay? We're finding the exact value of the cosine of 15 degrees. So the first thing I would think is, oh, cosine is just the x value at that place on the unit circle. And then hopefully you'd have a unit circle handy. Or one on the wall you could look at or whatever, okay? Or maybe you just have it memorized. So I'll go find 15 degrees. What the? It's not there. Okay, so these aren't the only angles in the universe, right? There's 31 degrees, 32 degrees, and so forth. So if it's not one of these special angles, then we need a different strategy. And the sum and difference formulas can help us to get to a lot of these angles, okay? Actually, eventually you could get to all of them with the sum and difference formulas. But so what I'm going to do is I'm going to find two special angles that I could use to add or subtract to make 15. Okay, so these are, and I'm not worrying about the formulas yet. I'll get to them in a second. But I'm using two special angles. And that just means it's two angles that are actually on this unit circle, okay? So I'm thinking 15 degrees. Well, what if I used, say, a 45 and a 30 together? If I did 45 minus 30, that would be 15 degrees, okay? So that's what I'm going to think. I'm going to think 15 degrees is equal to 45 degrees minus 30 degrees. And these two are special angles that I have on my unit circle, okay? So, next step, use a sum or difference identity. So, since I'm going to be subtracting here, I'm going to use a difference identity, and I've got cosine, so I'm going to use this difference identity, okay? So, for this problem, A is going to be 45, and B is going to be 30, okay? So, the cosine of 15 degrees, in other words, is going to be equal to the cosine of 45 minus 30 degrees, okay? So then my A and my B, sorry, I was off screen there a little bit. Here, I'll just set it up like that. I'm going to be using this formula up here, okay? So, let's see. I've got cosine of A times the cosine of B, all right? Cosine, that means cosine of 45 degrees times the cosine of 30 degrees. Okay, so that's that first section right there that I did. Okay, now I'm going to add that to the sine of A plus the sine of B. So the sine of 45 degrees times the sine of 30 degrees. Okay. These can be a pain to memorize, all these formulas, but I'm not asking you to memorize them at this point. I'm just asking you to use them, okay? So there's my setup, and now each one of these pieces, I can use the unit circle. So for my cosine, I'm just looking for the x value at those different places. For the sines, I'm looking for the y value at those different places, okay? All right, so let's go ahead and try this. So the cosine of 45 degrees, well, that's going to be root 2 over 2. That's the x value right there, right? And at 30 degrees, the x value is root 3 over 2. Okay? And then at 45 degrees, I'm looking at my y value now, which is root 2 over 2 again. And at 30 degrees, the y value is 1/2. Okay? So then I'll start to simplify. So let's see, I'm multiplying straight across. So a lot of times I see people write, oh, this is root 6 over 2. But it's not. You multiply multiply straight across on the bottom too. So this is root 6 over 4 and root 2 over 4. Okay? And then I'd want to combine this into one fraction, and happily I already have a common denominator, so that works out really nicely. Okay, And you know, there's no twins in here, so this is in simple radical form, and that's about as good as I can do. Okay. Now, you could test this with a calculator. I mean, I can put the cosine of 15 degrees into my calculator. It's going to give me a decimal. Let me make sure I am in degrees. Okay, so let's see. The cosine of 15 degrees. I've got this, but if you put this into your calculator, let's try it. Root 6. Let's add that to root 2, and then divide by 4. So I've got that same number still at the top of my calculator screen. That's the same thing. This is equivalent to 0.9659, right? But this one is exact. It said find the exact value, so I did that with one of those formulas. Okay. All right, so let's try this next one. I've got 105 now, so I'm thinking, okay, how can I make 105 is not on the unit circle itself, right? It goes from 90 to 120. It'd be somewhere in here. But I'm going to try to use these special angles to make 105. So I'm thinking 90 plus 30 would be 120. That's no good. Hey, maybe I can use the 45. How about 45 and 60? Those two together would make 105, right? So I can think, okay, cosine of 105 degrees, 105 degrees equals cosine of 45 degrees plus 60 degrees, like so. Okay, and then I've got my new A and B. This time it's I'm going to use one of the sum identities because I'm adding, right? Last time I was subtracting, so I used a difference formula, but now I'm using a sum formula. So I'm using the sum cosine formula, okay? So I'm looking back up to the top of my screen. I'm just going to write this cosine sum formula up here. Didn't leave myself enough space as usual. There is the formula, okay? So let's see. Got the cosine of A times the cosine of B. So that's the cosine of 45 degrees times the cosine of 60 degrees. Okay? Then I'm going to be subtracting, okay, sine of A times sine of B. Sine of 45 times the sine of 60 degrees. Okay, and just like the last problem, now I'll pull out my unit circle and I'll look at the x values for the cosines, I'll look at the y values for the sines, start plugging in those values. So 45 degrees, x value is root 2 over 2. At 60 degrees, x value is 1/2. At 45, my y is root 2 over 2. And at 60 degrees, the y value is root 3 over 2. Okay, so let's multiply everything together here. I got root 2 over 4 and root 6 over 4. Okay, and then got root 2 minus root 6 all over 4. Okay, and that is simplified. You'll notice you'll get a lot of answers that look very similar on these problems because any place on the unit circle, if it has a denominator, the denominator is 2. And there aren't that many different x values either, right? Or numerator values. So you get a lot of answers that look similar. Okay. And you know, you could take cosine of 105 degrees and the cosine of 15 degrees, for example, and get other angles using those with the original ones. Then it gets a lot more complicated. But if you're just using two of the original special angles, you keep getting answers that look almost the same. Okay. All right, so let's try some on the next page. Okay, on the next page, we're going to do the same kind of thing, except now we are going to be working in radians, which makes it a little trickier. It's just a little harder to get started. But once you get started, it's the same idea. Also, the tangent ones are more difficult, but just because if you look at the formula, you got fractions. There's just more going on with the tangent ones. So that's the nature of the tangent ones as well. Okay, so let's start with 11 pi over 2. So first thing I would check, I'd think to myself, okay, I'd just do y over x, but 11 pi over 12 isn't on here. So I can't just do the y over the x, okay? So I'm going to have to use one of these sum or difference identities, okay? And here's how I would usually handle this is I'm just going to kind of start thinking through, all right, how can I add to get 11 pi over 12? Well, what if I did pi over 12 plus 10 pi over 12? Okay, that would add to 11 pi over 12. And this would reduce to 5 pi over 6, right? 5 pi over 6 is on my unit circle. Why am I having trouble finding it? There it is. There's 5 pi over 6. Pi over 12 isn't on there, okay? So that means this is a dead end, so I'm just going to try another. So let's see, what if we had 2 pi over 12, and I'd have to add that to 9 pi over 12, right, to get that 11 pi in the numerator. Let's reduce these. Okay, this would be pi over 6 because everything on the unit circle is reduced. 3 goes into both of these, so this would be 3 pi over 4. Okay, so let's see if those are on here. Pi over 6, that one's on there. 3 pi over 4, so I hit a winner. Okay, this is not the only way you could break up 11 pi over 12 and find places on this unit circle. That's just the first one I found. So that's what I'm going to use, okay? So, yeah, let's go back. So, tangent of 11 pi over 12 is equivalent to the tangent of pi over 6 plus 3 pi over 4. Okay? So, now I'm going to have to use a tangent. I added to get mine. So I'm going to use that tangent formula from the previous page. Let me get that out there. I don't want to rewrite it, so I'm just going to put it there on the screen. Okay? So my A and B will be these two things, right? This is A, this is B. All right, so let's start plugging this into the formula. So I'm going to have a big fraction. I'm going to have the tangent of A plus the tangent of B. Okay, that's my numerator. And then for my denominator, I have 1 minus tangent of A times the tangent of B. Here's the tangent of A times the tangent of B. Okay, got everything plugged into this formula now. Okay, and now remember, we're just looking for y over x at each of these places. So now it'd be time to get out my unit circle, or just access it in your memory. All right, so pi over 6, I'm going to do 1/2 over root 3 over 2. So there's going to be a lot to deal with here. Okay, that was just this piece here. And then tangent of 3 pi over 4, that's going to be root 2 over 2 over negative root 2 over 2. There's my numerator. My denominator, tangent of pi over 6. We just did tangent of pi over 6 up there, right? So tangent of pi over 6 is 1/2 over root 3 over 2. And then tangent of 3 pi over 4, root 2 over 2 over negative root 2 over 2. Yikes. Okay, still a lot to do, but let's start working on this. Okay, there are some nice little shortcuts for simplifying these. Let me zoom in a little bit here. When you have the same denominator in the top and the fraction on the top and the bottom, yeah, you can write this as division and then multiplication, but what's going to happen is that, and this is going to be happening all the time because 2 is almost always my denominator on these, so it'll happen there, and there. Okay, so let's start looking at this again. I got 1 over root 3 plus root 2 over negative root 2. That's my numerator now. And that's my denominator, okay? You can tell this is going to take me some space, so I'm going to move up here, okay? So if I wrote this in simple radical form, just this piece, I'd multiply by root 3 over root 3, right? So that's going to be root 3 over 3. Okay, and then this part here is just negative 1 because it's something over its opposite. Okay, on the bottom, this is going to be root 3 over 3 again. Once you put it in simple radical form, and then this is negative 1 again. Okay. Okay. All right. So I still want to combine these up here. So I'm thinking of this as root 3 over 3. And then, you know, it's just minus 1. So minus, what am I doing? Minus 3 over 3. I was just writing the negative 1 as 3 over 3. I started to write a square root for some reason. Okay, on bottom, I'm going to write the 1 as 3 over 3 so that I can, and then a negative times a negative is positive, and I got it down to this. Okay, so now on top, we can combine that top fraction into root 3 minus 3 over 3. And the bottom fraction would be 3 plus root 3 over 3. Okay, and just like what happened in the beginning with canceling those denominators back here, we can cancel the denominators here as well. Okay, this is a bear of a problem, okay, because we're actually still, or this is not going to be in simple radical form. We're getting there, okay? Now, I still got a radical on the bottom. I can't just multiply by root 3 over root 3 because I'd have to distribute it, and I'd still have a radical in the denominator. So, here, let me separate this. This problem's way harder than the next one, by the way. Okay, so what I'm going to do next, then, is multiply by the conjugate of the denominator. This is something we did quite a while ago in here. But this is how I can get rid of the radical down there. I'm going to multiply by 3 minus root 3. And I have to do the same thing on the top then as well. Okay. All right. So I'm foiling this, right? So on top, that's first is going to be 3 root 3. Outer, root 3 times negative root 3. Sorry, I was off screen there. Root 3 times negative root 3, so that'll be negative root 9. Well, negative root 9 is negative 3, right? Inner is going to be negative 9. And last will be positive 3 root 3. That's all in the numerator, okay? Denominator, first is going to be 9. Outer and inner are opposites because I'd have negative 3 root 3 and positive 3 root 3. So I'm not going to bother with those. They'll cancel each other out. And then last, root 3 times negative root 3 would be negative root 9. Negative root 9 is going to be negative 3. Okay? No more denominator, no more radical in the denominator. Let's start simplifying. Okay? On top, let's see, I've got negative 12, and then 3 root 3 plus 3 root 3 would be 6 root 3. On bottom, I've got 6. Oh, this is looking pretty good, and I can actually still reduce further because all 3 of these terms, 6 goes into all 3 of those. So let's divide everything by 6. And this would be negative 2 plus root 3. Ouch, that's a tough one. Let's zoom out and admire all the work we did. Yes, look at that. Satisfying. Okay, and nice thing about this answer, even though it took forever, we could plug this into a calculator in radian mode, and we can plug this in and see if the decimal approximation is the same. So you can test your answer. Okay? All right, one more. Let's look at this sine equation. Okay, so let's see. 5 pi over 12. Let's see if that's on the unit circle. I'm suspecting it's not. Nope, it's not. So we're going to have to find a way to add to get. So let's try. I'm just kind of brainstorming here. Pi over 12 plus 4 pi over 12. Well, that'll give me pi over 12 and pi over 3. Pi over 3 is on there, but pi over 12 is not. Okay, so that's a dead end. So let's try 2 pi over 12 plus 3 pi over 12. Let's reduce both of these, pi over 6 and pi over 4. Those are both on there, so that's a winning combo. Okay, so that's the route I'm going to go. So sine of 5 pi over 12 is going to be equivalent to sine of pi over 6 plus pi over 4. Okay, so I'm going to go back and find my sine addition formula, which is right here. Okay, I don't want to rewrite it in the interest of time, but I'm doing sine A times cosine B. Okay, and I'm going to add that to cosine A times sine B. Just got it in there. Okay, and now I can use my unit circle, right? For sine, I'm going to be looking for y. Cosine is I'm looking for the x's. So I'm looking for those values on the unit circle. Okay, pi over 6, my y value is 1/2. Pi over 4, x value is root 2 over 2. Pi over 6, the x value is root 3 over 2. And pi over 4, the y value is root 2 over 2. Okay, and then we'll start simplifying. Combine those. Make sure you got no twins in the radicals. It's in simple radical form. No radical in the denominator. Not too bad. So the tangent ones are a lot tougher. Okay, and that's it for today. See you next time.